Hello everyone, I am Aseem, a PhD candidate at University of Waterloo, working with Kimon Fontlakis and Aukosh Jagannath, and I'm going to talk about graph convolution for semi-supervised classification. Let's begin with a brief overview of our contributions. First, we study how graph convolution operation affects the linear separability of a two-component Gaussian mixture model. Second, we show that the linear classifier obtained by minimizing the cross-entropy loss generalizes really well to data that is sampled from a different distribution. And finally, we illustrate our results through various experiments on both synthetic and real-world data. Now let's look at this simple picture that describes the core idea. We have a scatter plot of two-dimensional features sampled from a two-component distribution. And we can see here that it's really hard to separate the red and blue points since the overlap between the distributions is quite large. So how does graph convolution help here? Well, here's the scatter plot on the right, which is what we obtain after applying a graph convolution. Note that both the mean and the variance of the data have been reduced, but the variance is reduced by a larger amount. So the data points become separable. Now our goal is to quantify this improvement in separability through a simple and analyzable model that shows the key trade-offs arising in graph convolutions. So here's the model that we study. It's a two-component Gaussian mixture model coupled with a stochastic block model. There are two classes denoted C0 and C1 and n data points with feature vectors in d-dimensional space. These feature vectors have distributions associated with the class with different means mu and nu, but the same covariance sigma squared times identity. And then we have the adjacency matrix of the graph, which is sampled from a standard two-block stochastic block model. Then here we have our first result of the paper, where we show that with overwhelming probability, no hyperplane can separate a two-component Gaussian mixture model if the distance between the means is of the order of the standard deviation, which is sigma. Then under suitable assumptions, which I skip here for brevity, the graph convolution operation improves this threshold by a factor of the square root of the expected degree. To complete this argument, we also prove bounds on the training loss. When there's no graph and the distance between the means is below the said threshold, the loss is lower bounded by a constant that depends on the distance parameter k. While in the case where convolved data is separable, the loss is upper bounded by a function that decays exponentially with the dimension and the distance between the means. Then our next result proves that if the graph is not too sparse, more precisely if the degree is at least order log squared n, then even if we change the number of nodes, the parameters p and q for the test data set, we still get an exponential bound on the loss with high probability. And what that means is that the classifier learned through the optimization problem generalizes really well to unseen out of distribution data. This exponential bound, along with the plot below in the slide, shows that if there's more noise in the graph, which in our model translates to larger Q, then the loss increases and graph convolution is not too helpful. And that concludes the main contributions in our paper. Now let's look at a couple of questions that are potential future work. Note that we chose this two-component model and we analyze only a single layer network because of simplicity and feasibility of calculations. However, we would also like to note that we include the non-linearity in standard neural networks into our analysis. So naturally, one possible question we'd like to explore and what we'd like to do is extend our analysis and talk about separability and generalization for the multi-class setting and for deeper GCNs. So one possible direction is to consider a model where the data is non-linearly separable. So the classifier is not a simple hyperplane, but a more complicated function that cannot be learned by a single layer. So that marks the end of this talk. Thanks.